Okay, I want to kind of quickly demonstrate what I mean by fitting a straight line visually to a bunch of data points. Now, the author at the text we're presently using, and I really like the author and I really like his text, but I disagree with him on this, often says in the instructions for some of these problems, just go from the first point to the last point. And that ignores all the other points. It gives no weight to all the other points, and it just kind of goes against the meaning of what it means to fit a line to a set of data. What we want to do is, and this isn't quite right either, but it's really tricky to do what you really ought to do. It's really difficult to visualize. So what I'm going to say is our way of doing that in this course is going to be to minimize the distance of the line from the points, to minimize the average distance of the line from the points. So let's see, we can see that if I go from the first point to the last point, there are way more points above the line and further above the line than there are points below the line. So that's really not a good idea. Or if we regard this as the last point and this is the first point, well, that one actually would work out pretty well. If this is the first point and that up there is the last point, that one doesn't work out so hot. Okay, well, what we want to do is, though, we don't want to go through any of the points. Our best line is never going to go through our data points, or almost never. It would be very rare that that would happen. So that I'm going to say a line right about there maybe fits the data points better than most, okay? It minimizes the average distance of the line from the points. And I'm not going to go into a lot of detail on that. I'm just going to say, okay, well, let's see, I think my line went through about here and here when I had the rubber band stretched out. And let's see how that does. Okay, well, I kind of didn't draw the line exactly where I wanted to. And it didn't do a really great job. There are only 3 points below the line. There are 1, 2, 3, 4, 5 points above the line. 1 point that's almost too close to tell. So the line should have been a little bit higher. And also, we're trying to minimize the distance. That's a pretty big distance right there. And actually, we're talking about the distance above or below the line. So, you know, that's a pretty big distance. That's bigger than all 3 of the distances these points are below the line all by itself. So that's not a good line, but if we raise it a little bit, maybe we'll have a good one. Now, I will mention that what we really try to do is minimize the squared distance of the points, but that's more complicated than anything I want to talk about in a course at this introductory level. Now, the first set of points you're asked to plot and fit a line to it's the calories in candy bar versus the, no, actually it's not calories in candy bar, it's just a set of points. So let's see, we have a point here, point here, point here, and there's another point that kind of got obliterated. Well, anyhow, we graphed the 4 points, and we fit what we thought was the best line. And then to get the equation of the line, we take 2 points on the line, never using data points, taking 2 points on the line and calculating the slope based on those 2 points, and then hopefully the line goes through the y-axis. Hopefully we're close enough to the y-axis to extend our line through the y-axis so that we can read our y-intercept, or alternatively our x-intercept. Okay, but the y-intercept is going to be very handy because, of course, your equation is y equals mx plus b. If we know the y-intercept, we have b, and once we calculate the slope of our line, we'll be able to write the equation. Okay, well, for this line, again, we're going to take 2 points on the line. Okay, so I estimate this point, when x equals 10, to be to have a y-coordinate of about 22.5. I extended the line till it hit the x-axis, so I took the point -5, 0, which is where we estimated the line hit the x-axis. as the other point, and then we calculate the slope based on these 2 points. Well, from this point to this point, the rise is from 0 to 22.5. That's a rise of 22.5. And the run is from negative 0.5 to 10. That's a run of 10.5. And people were quick to tell me that. So I think everybody understood this pretty well. Now, if I divide that, I get approximately 2.1. That's going to be the slope of our straight line. The y-intercept, well, we hit the y-axis here. Now, this is 5. It looks like that's probably between 1 and 2. I'm going to say the y-intercept is 1.5. So now we have our equation, y equals 2.1x plus 1.5. And that's our model for this function. Now I asked people to do that in class, and everybody got slopes between the slope I got. Most people got slopes a little higher, but everybody got slopes between 2.1 and 2.6. So those slopes pretty well agreed. And remember, there's leeway. Who knows? I can't tell you who did the best job of fitting the line. Now, a lot of people had really tiny graphs, and it's going to be more difficult to get a good result with a really tiny graph. But again, everybody had results that were fairly consistent with everybody else's. So I think people did pretty well with this exercise. Okay, now, you didn't see the set of points, but these white dots are the points. And my question is, does a straight line fit those dots, or does maybe some kind of a smooth curve fit the dots better? Do they fit, which fits the trend of the data? And in this case, it's kind of ambiguous. You can't really tell which is better. The straight line looks like it does about as well as the curve, although I think maybe the curve beats it a little bit. But does this really represent data that indicates a curved trend, or does it represent a straight trend? That can be difficult to determine, but that is one of the questions you're going to want to answer. Now, over here we have calories versus the weight of a candy bar, the weight in tenths of an ounce. Okay, so we have 5/10 of an ounce, 10/10 of an ounce, of course that'd be 1 ounce, 25/10 of an ounce, that would be 2.5 ounces. These dot X's here represent the points we get on the graph. It looks like they're kind of 2 clusters, one cluster here, one cluster here. Now, I didn't look at actual data. It's Halloween. I'm going to get some good full-size candy bars, because I always give out full-size candy bars to everybody who comes by the house except students, because I don't want people. Well, I would certainly give candy bars to students too. But another perk is I always buy way too many, because I want to be sure I don't run out and disappoint people. So I bring those into class the next week, so people get candy bars anyway. Okay, well, digression aside, there's probably one type of candy bar that has probably contains more fat and sugar than some other group of candy bars. I've been actually kind of researched that. I'm going to look at the calorie contents of different candy bars and get my own data. I kind of based this on data similar to the data in one of the problems in the textbook. Not sure that problem would give you this kind of grouping. Anyhow, in fitting the straight line, I pretty much just kind of went through the middle of both of these groups. Okay, there might be a better way to get a better result. And I'll also mention that you can put this into your handheld calculator or into a computer spreadsheet, for example, and get the best fit line. Okay, you can calculate the best fit line, and I could explain to you how to do that, but this is not a calculus course. This is being done for a college algebra course right now, although it would apply to many other courses. Okay, I'll stop rambling and we'll go on here now. So we've got our line, and I choose 2 points on the line. So I just chose this point arbitrarily, projected down here, said that looks like about 22. Looks a little bit more like 21.5, but I just went with 22, and 300 over here, meaning we have 22/10 of an ounce, or a 2.2 ounce candy bar with 300 calories. Now that's not an actual candy bar, that's just on our straight line approximation. And then I used the y-intercept, and I estimated that to be 0, -30. If this is 100 here, then this looks like it might be about -30. Actually, as I look at it a little closer, it's maybe like -40, but that's okay. You understand what's going on. So we get the slope of our line, which is going to be 330 over 22, or 15. And the y-intercept is -30. So our function is what? Well, it's like y versus x, but I use C for calories and M for mass. Probably should have used W for weight, but originally the information in the textbook gave you masses and called them weights. So I'm just being consistent by using the wrong word. You don't have to worry about that. Okay, that's mass, or it's weight. And really M is kind of a confusing letter to use here, so I am going to change that to W. So using C and W, I get the equation C equals 15W minus 30, 15 being the slope and -30 being the vertical intercept, in this case the C intercept, like the y-intercept. Then we say, okay, well, if W is 30, okay, that would correspond to 30/10 of a gram, okay, or a 3-gram candy bar. That's getting up, that's 3/4 of a quarter pounder. So that's a pretty substantial candy bar. Now, back when I was a kid, you could get candy bars of that size. It was kind of a standard size, even bigger than that. But they've been shrunk, and that's probably beneficial. Okay, so if W is 30, meaning 30/10 of an ounce, what would the number of calories be? Be 15 times 30 minus 30, because you plug in 30 for the W. 15 times 30 minus 30, 420. Interpretation, 420 calories in a candy bar of 30/10 of an ounce, or 3 ounces. Now we might want to do just a little more and interpret the slope, okay? And to do that, we're going to just put the units on the 330 and the 22. Now what does the 330 really represent? It's a difference between -30 on the calorie axis and 300. So it represents a change of 330 calories. So that represents 330 calories. And the run from 0 to 22.5 or 22 represents change in the weight of a candy bar, 22/10 of an ounce. I'm going to use TOZ, TOZ, for tenths of an ounce. When we divide it out, we get 15 calories per tenth of an ounce. That means that every tenth of an ounce of a candy bar, of a typical candy bar, is going to tend to be about 15 calories. And that would be then about 150 calories per ounce, wouldn't it? Another characteristic of this graph, we would really expect to get 0 calories if we had 0 weight. So we would expect the graph to go through the origin. Well, this graph comes very close to going through the origin, so that the data we get here is consistent with the idea that we would have 0 calories for 0 weight. Now, we didn't exactly go through the origin, we didn't exactly go through 0, 0, but that's just maybe a little glitch in the way we fit the line. If you fit a good line to this stuff, you're going to come close to 0, 0. And of course, the calorie contents, these are different types of candy bars, different manufacturers, so there's leeway, there's uncertainty in just where these points would lie. So you wouldn't expect the actual graph based on actual candy bars to exactly go through 0, 0, but we do tend to think that it will come close to 0, 0.